All right, so in this lesson, I'm going to be discussing average atomic mass. So remember, average atomic mass is simply a weighted average of all of the naturally occurring isotopes for a specific atom. So what exactly does that mean? What is a weighted average? Okay? Keep in mind really quickly as we go through these, all of the values for mass that you see on the periodic table, those are average atomic masses. So if I ask you to calculate the average atomic mass, you can easily double check yourself to make sure that your answer is right by looking at the periodic table. Now keep in mind some of the answers might be slightly off due to rounding, but they should be pretty dang close. So let's look at the first example to really understand what a weighted average is. So it says naturally occurring europium consists of two isotopes with a mass of 51 and 53. Europium-51 has an abundance of 48.03% and europium-153 has an abundance of 51.97%. What is the average atomic mass of europium? All right, so traditional averages would have you simply add 51 and 53 and then divide by 2. But the reason why we have to do a weighted average is because the typical average that you do of adding them together and dividing by 2 assumes that they contribute equally, 50-50. But they clearly don't, right? One contributes 48.03% of all naturally occurring isotopes, while the other one contributes 51.97%. So what we actually need to do is a weighted average. So the first thing I need to do before I actually calculate it is I need to take my two percentages, 48.03% and 51.97%, and I need to convert those into decimals. So the way that I do that is I move my decimal place 2 places to the left. And the reason why I do that, percent means per 100, so I'm literally just dividing by 100. Okay? Now I can find my weighted average. So I'm going to take the first mass number, which is 151, and I'm going to multiply it by its percent abundance as a decimal, so 0.4803. I'm going to add to that the next mass number, which is 153, and multiply by its percent abundance, which is 0.5197. Okay? And that will give me my answer. So I'm going to multiply 151 by 0.4803 plus 153 times 0.5197, and the value I get for the average atomic mass, rounding to 2 decimal places, like I'm being asked to do, is 152.04. Now the units for average atomic mass are AMU. That is a relative unit. Carbon was actually used to define that unit. But the reason why we use AMU is because, remember, your mass numbers are determined by the number of protons and neutrons. So 152, it's not going to be 152 grams, because otherwise, if we used grams to represent the number of protons and the number of neutrons, the value for grams would be really, really small. And so in the interest of keeping these reasonable numbers, and you'll actually see how we use it in future units even further, we're going to use the unit AMU, atomic mass unit. So a nice way to double check yourself to make sure you are correct, go to europium on the periodic table. It's actually in that bottom 2 rows. Its average atomic mass is 151.97. Okay, so I am just 0.07 off. So I'm okay with that value. Let's go to the next problem. Calculate the percent abundance of each copper isotope based on copper's average atomic mass of 63.55. So it now is asking me to find the percent abundance by giving me the average atomic mass. So if you think about it, since there are only 2 isotopes of copper-63 and copper-65, their percent abundances need to add up to 100%. Since what I'm going to be using in my formula for calculating average atomic mass are decimals, I'm going to be using decimals for my average atomic mass, they're going to add up to 1. If I said the percent abundance of copper, 63, was X, what would the percent abundance of copper, 65, have to be in order to get a value of 1? Well, if I subtract X from both sides, what I find is that my percent abundance is 1 minus X. So now what I can do is actually plug in these 2 variables, X and 1 minus X, into my average atomic mass formula to determine the percent abundance of each isotope. So copper-63, we said, has a percent abundance of X. Copper-65 has a percent abundance of 1 minus X. And the average atomic mass of those 2 isotopes is 63.55. Okay? So now I'm going to actually do out the algebra. So 63x I'm going to distribute the 65 to both the 1 and the minus x. So 65 times negative x gives me negative 65x. And that equals 63.55. Okay? I'm going to combine like terms. So say 63x minus 65x gives me negative 2x plus 65 equals 63.55. I'm going to subtract 65 from both sides. Okay, so what I get here is that negative 2x equals negative 1.45. I'm going to divide both sides by negative 2 now. And so the value that I get for x is 0.725. Okay, keep in mind it asks for 3 sig figs. So this is my percent as a decimal. So the actual percent when I move my decimal place 2 places will be 72.5%. That's 3 sig figs. So copper 63 has a percent abundance of 72.5%. Well, the rest of it is going to be copper 65. So how do I determine the percent abundance? 100 minus 72.5, and that'll give me 27.5%. Okay. And those are my percent abundances. Now, to double check yourself, super easy. You can always take 63, multiply it by its percent abundance as a decimal, so 0.725, and add to that 65 times its percent abundance, 0.275, and make sure that it truly is, the average atomic mass is truly 63.55, right? Because that's how we do a weighted average. So actually find the weighted average of these values of your 63 and 65 with their percent abundances that you just calculated, and make sure that it really is 63.55, and it is. Let's look at number 3. Using the following data, calculate the average atomic mass of magnesium. Okay, so notice I give you your mass numbers up top. So 24, 25, and 26 are the mass numbers. I'm going to move my decimal places 2 places. So 1, 2, 1, 2, and 1, 2. So this is just a traditional weighted average problem. So I'm going to take 24, multiply by its percent abundance, 0.7870. Add to that 25 times its percent abundance, which is 1013. Add to that 26 times its percent abundance, which is, as a decimal, 0.1117. Okay? And I'm going to multiply all of these by their percent abundances and add them together. And what I end up getting is 24, rounded to 2 decimal places, 24.32. And remember, for average atomic mass, my units are AMU. Okay. Now, nice way to check yourself, go to your periodic table, look at magnesium, and you can see that the average atomic mass, according to the periodic table, for magnesium is 24.30, so I'm pretty dang close.